It's lessons learned using a Mission Control Center, Geoscience console for NASA's NextSTEP Habitation module, crew testing, which is given by Evans et al.
My name is Michael Evans. I'm a planetary scientist at NASA Johnson Space Center. I'm going to talk about an activity we held over a 2-year period where we were evaluating gateway habitation modules and the lessons learned from that activity. Next slide, please. The Gateway Habitation Module program was begun before Artemis. It was a NextSTEP program, which is a joint commercial government implementation plan to do exploration. A BAA was announced in 2015 to ask contractors to create concept HAB modules. The JSC team here built 2 internal HAB modules to build a ground team so that we could then do the evaluation of these contractor modules, which were then conducted in 2018 and 2019. And then NASA, as you all know, awarded a contract to Northrop Grumman to build a miniature HAB module based upon their Cygnus spacecraft in 2019. Next slide, please. What we've talked about at this workshop is broadly EVA-based ground science. The work that this team did over this 2-year process was on Gateway in lunar orbit. And the first thing I want to know is that we use the word science too broadly. In my environment, when we were testing, we had biologists, we had material scientists, we had people doing cellular research. Science is much broader than geology and geophysics. And so when we call it a science backroom, I prefer to call it a geoscience backroom. So the console that I built in the MCC is called GeoSci. Recognizing that there were times when I was on console when we had somebody doing cellular research, somebody doing a telescope observation, doing glove box operations in Gateway, had somebody doing an astronaut biology experiment on their muscles, and all of that is science. It is not just EVA traverses. So there's a whole world of science, and when we talk about science support, it needs to be broader than just the geological sciences. However, speaking on that, we learned many lessons from this activity. Next slide, please. Gateway evolved rapidly as this time frame was going on. We started in 2017 with something called Deep Space Gateway, which had no lander. Then we went to the LOP-G briefly, and then we had a giant gateway. And then all of a sudden, Gateway got slashed and it turned into a phone booth. So what you see in the lower right is where we are now. And we were testing throughout all of this. And we had to write procedures and modify procedures based upon whatever contractor capabilities were being delivered to us. And we ran the Mission Control Center team running procedures based upon whatever hardware and software the contractors provided. Next slide, please. We had 5 different contractors prototyping different things. We were located at different, all of them were located at different locations around the United States. Mission Control stayed in Houston, Texas, and we figured out how to make that seamless. Next slide, please. This is the evolution of the GeoSci console. We started initially in 2017 with just a single console on the upper left, cohabitated with the SIM team that grew into a remote environment SIM team. But what we really wanted with this activity was to create a real mission control center. For the first time since Desert Rats that we heard David Crane talk about earlier, we actually had in Building 30 in Johnson Space Center a full mission control team with the full support of flight ops. We had Capcom flight. Most of us had flight experience from shuttle and station. So we ran this as flight realistic as we possibly could using the resources at Johnson Space Center. Next slide, please. The procedures that I wrote were various. Like I said, I did not do EVAs. We had no airlock, but we did good geoscience. We had telescope observations. We had sample processing. We had simulation for samples being delivered from the lunar surface to the gateway that were then packaged in a gateway glove box. I wish we had the glove box that Cindy Evans talked about earlier. Ours was a much lower fidelity model. We did science experiments inside and outside the gateway using robotics, and we drove a rover on the surface using telerobotics, guiding the crew and where to find samples. Next slide, please. So these are some of the images from what I ran on what I call GeoSci. You can see the imagery from the rover. There's a gateway dust collector, which was deployed on the outer hull of the gateway. We had sample return through a science airlock. We were doing solar observations to warn the crew if there was a radiation event or a mass ejection on the sun that triggered a emergency drill in the gateway where the crew had to hunker down to save themselves from a dangerous situation. We had a glove box and we had windows so that the crew was doing observations and geologic science and telerobotics and robotics ops all at the same time, all under geoscience. Next slide, please. The big thing about this simulation was we were actually in the Building 30 of Johnson Space Center. Getting data into the Mission Control Center had a series of hurdles that we had to accomplish because of the tight firewalls around the Mission Control Center itself. Clearly, we had to identify our voice requirements, our camera requirements, and our telemetry requirements. This is something necessary that the Artemis program is going to have to do for both Gateway and the surface, and it will have to grow over time because we learned it's easy to saturate your bandwidth. We had many problems. It took us a full year to figure out how to get data into the control center and manage cameras and manage telemetry flow of data and commanding. And voice software was difficult using our different loops and how many people could talk on a loop at the same time. This is all very valuable information that's done as you're in the design phase of a mission so that you can drive requirements on the ground hardware and on the vehicle itself. Next slide, please. So my lessons learned are basically in two categories. The first page is broad. The second page is specific to each of the procedures. The first thing I've already hit on, I think the term science is too broad. We keep talking about science. We are geoscience. There's biological science, there's material science. I prefer to categorize the work that I do as geoscience and not be so broad. Secondly, the thing that we learned about having SMEs, subject matter experts, in the actual Mission Control Center, there is a culture to FOD, flight ops. It is something I learned over a very long career before I became a scientist. It is something you can learn as a scientist, but it takes years. It's not just learning how to talk on a loop. And the interaction between flight and Capcom and an SME on various consoles that are manned infrequently, but when they're there, they're absolutely necessary. MCC has a long history of using partially manned consoles. We did it on the shuttle with Booster. We did it with Surgeon. On ISS, we use Topo. We have consoles that are empty part of the time, but when you need them, that SME is sitting in the front row, and that is an important key. You need to be able to look at flight, talk to flight, interact with your other flight controllers as you're doing your critical activities. The second thing is procedures. We wrote flight procedures exactly as we would on a shuttle or station mission. That is a very complex, difficult process. It takes a year to write a good procedure. I was humbled many times on what I thought was a perfect procedure that we gave to a crew to execute, and they promptly broke it. Or they didn't understand what I wrote, or we had hardware software failure that I assumed that wasn't correctly documented. Writing procedures for a crew that has to be very efficient and very clean takes a lot of work by a lot of people. And you have to guide a whole lot of things that I've documented. You need templates, you need terminology, you need verification steps, you need all that. The other thing I heard earlier in the talk was the use of electronic tablets. We used electronic tablets. Electronic tablets fail. What do you do when your crew has no electronics? Then you go to paper. You don't have paper, the crew is going to make up stuff. So you still need paper backup for your procedures. Next slide, please. The second part of my lessons learned are specifics. One of the key things that Dean Epler and I worked on, thank you, Dean, for your background. You need a window if you're going to be using an arm or to monitor prox ops with visiting vehicles. If you're driving on the surface with telerobotics, the crew gets lost on a featureless surface. You need to add navigation markers or give them a God's eye view, because I could tell them to go look at a rock and every rock looks the same on a flat, even surface. So laser rangefinder helped. We used the sun to help watch for flares. We added experiments based upon our experience. We built the cosmic dust collector to go on the outside of the hull. Of course, you need a science airlock and an arm to do that. Sample transfer is a very important thing for an orbiting vehicle. We learned a lot about that and using experiments inside. So it was an excellent activity. It was not traverse-based, so all of this science needs to be added to the discussions as we're talking about doing lunar surface traverses. Thank you.
Thank you very much.